All right, guys, here we go again. We're in chapter 17, and we're getting ready to talk about titrations. Okay? Now, a titration is a process of adding a solution of known concentration and volume to a solution of known volume but unknown concentration, so that we can determine the concentration of the solution that we don't know the concentration of. Okay? There are many different types of titrations. We're going to concentrate in on acid-base titrations because we're playing with acids and bases. If you are lucky enough or cursed enough to have to take analytical chemistry, you'll do a lot of different types of titrations. Now, in a titration, there's something called an equivalency point. This is the point in the reaction where the moles of, in our case, hydronium ions are going to equal the moles of hydroxide ions. So it might be hydronium ions in the one container equal the moles of hydroxide ions added. Now, there are two methods we can use to determine the equivalency point. One is to use an indicator, okay, and we'll do that in lab, which is a molecule that changes color depending on whether there's excess acid or excess base present. The point at which the color changes is called an endpoint. And if you're doing your titration very, very, very carefully, the endpoint is very close to the equivalence point. At the equivalence point for the titration of a monoprotic single hydrogen strong acid and a monoprotic, a monohydroxy strong base, molarity of the acid times volume of the acid equals molarity base times the volume of the base. We're going to do that in lab. And in fact, we'll probably have done it at least once before you watch this video. Okay? A second method to determine the equivalency point and also get a little bit more information out is to use a titration curve and a pH meter. A titration curve is a graph of pH versus volume of known concentration reactant added. At the equivalency point of a strong acid, strong base titration, the pH is 7. If you're doing a titration curve, you have to plot volume of the substance added versus pH. Okay, so volume of whatever added is your x-axis, pH is your y-axis, and you can also use this graph to determine an equivalency point, or you can use it to determine some other things depending on what kind of acid and what kind of base we're looking at. So we're going to look at several different types of titration curves. We're going to start with the simplest titration curve, which is a strong acid, strong base titration curve. Now, here's a picture of a strong acid, strong base titration curve. I say strong acid, strong base because the acid is what's in the flask to begin with, and we're slowly adding base. So notice it says volume of base added and the pH. Now here's the graph. A strong acid, strong base titration curve is always going to start out with a very low pH. It's going to start just gradually rising, and then you get this region of very rapid rise. So notice that we go 39, 39.5, 39.75, 39.90, 39.95, 39.99, 40. Notice that huge jump, 4.90 to 7. And then we go to 40.01 and it jumps to 9.10. Okay? This is called the region of rapid rise. The equivalency point is always in the middle of the region of rapid rise. This case is going to be at pH 7. Okay? And it's the equivalency point. On this side, okay, the acid side, phenolphthalein is clear. On the base side, it's a brilliant pink. And you can see that 1/100th of a drop over the equivalency point, we've gone pink. And that's how we know that we've reached our endpoint. and it's within 1/100th of a milliliter. Close enough. Okay? Now, there are other acids and bases out there besides strong acids and strong bases. Let's talk about weak acids and strong bases. When we have a weak acid titrated with a strong base, we get a different behavior. Okay? So let's look at the reaction of a strong base with a weak acid. So if I had HF and I'm reacting with NaOH, my outcome, my products are going to be water and fluoride ions and sodium ions. Now, the sodium ion is a neutral cation. The fluoride ion is a basic anion. So as I'm adding NaOH, before I reach the equivalency point, when the reaction happens, this one goes 100%, and in solution, I'm going to be left with some HF and some fluoride ion. So I'm going to be left with a weak acid and its conjugate weak base in solution. Get this back down here. Okay. I hate this screen. Okay, let me get this back where I want it. So, I'm going to have a weak acid and its conjugate weak base. Okay? So that means I've now created a buffer solution. So by partially titrating, adding some strong base to a weak acid, you can create a buffer solution. And now the solution is going to try to resist change in pH as I add more NaOH until all of the HF is used up. So let's look at a pretty graph. Okay, so here's the graph of a weak acid being titrated with a strong base. Now, this dotted line is what a strong acid, strong base titration curve looks like. This is a weak acid, strong base. Notice the pH starts off much higher with 0 milliliters of base added. And notice instead of just gradually rising, we got this kind of little hump, and then it very, very slowly rises. Okay? This is the buffer region where it's resisting change in pH. And then we're going to get a rapid rise, and then past the equivalency point, notice that the strong acid, strong base curve and the weak acid, strong base curve are identical. And that's because past the equivalency point, you have a strong acid solution. Strong base solution, excuse me. Notice also here that the equivalency point is greater than 7. Because at the equivalency point, all of the weak acid has been converted over to conjugate base. So I have a weak base solution. Okay? We have a weak base solution. Now, for a weak acid, strong base titration curve, we want to also talk about the half titrated point. Okay, let me show you the half titrated point. At half titrated, the concentration of the weak acid equals the concentration of the weak base. It's conjugate weak base. So at half titrated, pH is going to equal pKa. So by doing a titration of a weak acid with a strong base and figuring out the half titrated point, you can determine the pKa for that acid, and from the pKa you can get the Ka. Okay? All right, now All right. Here is a weak base being titrated with a strong acid. Okay, notice the pH starts high, and instead of the pH increasing as we add in material, the pH decreases because I'm adding in acid. Okay, instead of having a region of rapid rise, we have a region of rapid fall. And the equivalency point is in the middle of that region of rapid fall. We would see a change in the color if we were using an indicator. And again, half titrated is an important point because the pH at half titrated is equal to the pKa of the conjugate weak acid. If I get Ka for the weak acid, I can get Kb for its related conjugate base. But this is what a weak base, strong acid curve looks like. Now, these are very handy. They're used quite a bit in labs. And one of the things that we need to be able to do, let me talk about a polyprotic acid before what we're going to do with these. Here is a polyprotic acid. Last chapter I told you that the polyprotic acids give up their hydrogens one at a time, and that first hydrogen is removed and equilibrium is established, and then what little bit of the second hydrogen there is can be removed, and so on and so forth. If you look at this graph, it's a polyprotic acid, H2SO3, being titrated with sodium hydroxide. So it's a weak acid being titrated with a strong base, but it's a polyprotic acid. I want you to notice that there are two regions of rapid rise corresponding to the two donatable hydrogens. And there are two half titrated points. Half titrated for the first hydrogen, half titrated for the second hydrogen. Half titrated for the first hydrogen gives us the pKa for the first acid removal, and the pKa at the second one give the pH at the second half titrated is the pKa for the second hydrogen to be removed. But there'll be two equivalency points. If there were three removable hydrogens, we'd see three regions of rapid rise and three equivalency points, three half titrated points. Okay? But this is what a polyprotic acid looks like. All right. Now, one of the things that all chemistry books require you to be able to do is calculate the points in a titration curve, knowing the concentration of the acid and the base and volumes. So it's creating a titration curve without physically doing the titration. All right? So it's an artificial titration curve. So we're going to look at all the points and how we calculate. Now guys, don't think about this as something new. This is something you've been doing. We're just putting everything together in one big pot. So we're going to start out with a strong acid, strong base titration curve. Then we're going to look at a weak acid, strong base titration curve. And those are the only two that we're going to look at. Now, a strong acid, strong base titration curve, we're going to be given volumes of the acid and the base and the concentration of each. So we're going to determine the pH and the moles of acid and moles of base at different points along the addition of the base. So the first thing we do is we're going to determine the millimoles of acid and millimoles of base. Millimoles of acid initially, which is going to be all the millimoles of acid we're going to have in there, and it's going to be the molality of the acid, and the molarity of the acid times the volume in milliliters. Millimoles of base added as the molarity of the base times the volume of the base added in milliliters. Next we're going to do after we get millimoles of acid and millimoles of base is to compare the millimoles of acid and millimoles of base. We're at the initial point of the reaction if our volume of base is 0. So that our millimoles of base is 0. We're pre-equivalency point if millimoles of acid is greater than millimoles of base. We're at the equivalency point when the millimoles of acid equal the millimoles of base. And we're post-equivalency point if millimoles of acid initially is less than millimoles of base added. Okay? So in the titration curve, we're always going to talk about the 4 regions. The initial point, pre-equivalency point, equivalency point, post-equivalency point. All right. The initial point, no base added. For a strong acid, strong base titration curve, the pH is just going to be the negative log of the hydronium ion concentration, which is negative log of the strong acid concentration initially. Guys, remember, definition of strong acid, 100% of it's converted to hydronium ions in water. Pre-equivalency point, I'm going to have to find out how many millimoles of acid are left over. So unreacted millimoles of acid equals millimoles of acid initially minus millimoles of base added. Our new volume is volume of acid plus volume of base added in milliliters. And our new molarity of our acid is our unreacted moles of acid divided by the new volume of the solution. And then the pH is just going to equal the negative log of the acid concentration. Okay? At the equivalency point, millimoles of acid equals millimoles of base, and in a strong acid, strong base titration, the pH is 7. No more calculation needed. Post-equivalency point, now millimoles of base is greater than millimoles of acid, so we're going to have unreacted base. So unreacted millimoles of base equals millimoles of base added minus millimoles of acid initially. The concentration, the molarity of excess base, is the unreacted millimoles of base divided by the new volume. Okay? And the POH went a little too far, sorry guys. Okay. POH is the negative log of the hydroxide ion concentration. It's just the negative log of the base. And pH is going to be 14 minus POH. So let's run through a problem. I can't run through a problem. Well, no, I can't because I didn't. Well, I can do some of it. Okay. Let's take 20 milliliters, 20 milliliters of 0.10 molar HCl, and I'm going to titrate with 0.10 molar NaOH. Okay, so our initial point, 0.00 milliliters NaOH added. pH is just going to be the negative log of 0.10. Okay, that should be a pH of 1, but I'm going to double check it. Yep, pH of 1. So it'd be 1.00. Okay, now let's add 7 milliliters of NaOH. Okay? So our millimoles of acid is going to be 20 milliliters times 0.10, which is 2.00 millimoles. Our millimoles of base equals 7.00 milliliters times 0.10. So that gives me 0.700 millimoles of base. Millimoles of acid is greater than millimoles of base. So we're pre-equivalency point, and we're going to have excess acid. Okay, so since I've got excess acid, my millimoles of acid in excess equals 2.00 minus 0.700, which is 1.30. So the molarity of the acid is going to be 1.30 divided by the new volume, which is 27 milliliters. So 1.3, clear. 1.3 divided by 27 gives me a concentration here of 0.048. Let's see, 481. So our pH here is just going to be the negative log of 0.0481. Zero point 481 in brackets. So I get a pH of 1.32. Okay? Now, at the equivalency point, okay, and we'll give myself some room here. When we've added milliliters of NaOH. Now our millimoles of acid, they don't change. It was 2. But now our millimoles of base is 20 times 0.100, so it's also 2. This is the equivalency point. pH then is going to equal 7. Okay? Once I know I'm at the equivalency point, strong acid, strong base, I go immediately to 7 as the pH. Now, let's add 25 milliliters of base. So now our millimoles of base is 25 milliliters times 0.100. So that's 2.50 millimoles. Okay, so now we're post equivalency point because millimoles of base is greater than millimoles of acid. So our excess base is just going to be 2.50 minus 2, 0.50. And the molarity of the base is just going to be 0.50 divided by the new volume, 45 milliliters. So 0.5 divided by 45, its concentration is 0.011 molar. So our POH is 1.96. So our pH is 12.07. I mean, it's 12.04. Okay? So there are the points in a strong acid, strong base titration curve. And we've worked all the way through an example. Now, let's talk about a weak acid, strong base titration curve. Now again, we've got the initial point, the pre-equivalency point, the equivalency point, and the post-equivalency point. We're going to have a little bit of change to our concentration because we're dealing with a weak acid now instead of a strong acid. So at the initial point, 0 milliliters of base have been added. All we have is a weak acid solution. So you need Ka to find the hydronium ion concentration. If the Ka is small enough until you're going to make the assumption, we can kind of do a quickie. Okay, we're going to take a shortcut. When we make the assumption, all the math that we do comes down to the hydronium ion concentration is equal to Ka times the acid initial concentration, all raised to the square root. Well, all raised to the 1/2 power, that's the square root. pH equals the negative log then of hydronium ion concentration. Pre-equivalency point, millimoles of acid initially is greater than millimoles of base added. We're in the buffer region. The millimoles of weak acid is going to be molarity of the acid times volume in acid initially. Millimoles of base made is the molarity of the strong base times the volume of the strong base added. Unreacted millimoles of acid. What's going to be left is millimoles of acid initially minus millimoles of base added. And then we use the Henderson-Hasselbalch equation. Okay? We're going to say pH equals pKa plus the log of millimoles of base divided by millimoles of acid. Sorry guys, got a little carried away there. Now, at the equivalency point, we cannot automatically say for a weak acid, strong base titration that the pH is 7. Because at this point, all of the weak acid has been converted to conjugate weak base, and what we now have is a weak base solution. And we have the reaction, the anion weak base plus water going to conjugate weak acid and the hydroxide ion. This conjugate weak acid is a newly minted acid molecule, okay? Not one of the originals. So the molarity of the weak base is just the millimoles of weak base added divided by the new volume of the solution. Okay? And Kb for that weak acid is Kw divided by Ka, 1.00 times 10 to the minus 14 divided by Ka. And making assumptions, the hydroxide ion concentration is just going to equal the molarity of the weak base times Kb all raised to the 1/2 power. The hydroxide ion concentration is just the negative log of hydroxide ion. And pH is going to be 14 minus POH. post-equivalency point, your pH depends on your excess strong base. So millimoles of excess strong base is going to be millimoles of base added minus millimoles of acid initially, which gives us the molarity of our excess base is millimoles of excess base divided by the new volume. And pH is just going to equal the negative log of hydroxide ion concentration, which is the negative log of the strong base in excess. And pH is going to be 14 minus POH. Okay? So now it's time to do an example problem. All right? And when we do this example problem, we'll be done with our acids and bases, and we'll start talking about slightly soluble salts. All right, titration of a weak acid with a strong base. So we're going to start out with 20 milliliters of a 0.10 molar HClO solution, hypochlorous acid. We're going to titrate with 0.10 molar NaOH. The Ka for the acid is 2.9 times 10 to the minus 8. So if we think about the initial point, 0 milliliters of base added. Okay? Then the pH is just going to, well, the hydronium ion concentration is going to be Ka 2.9 times 10 to the minus 8 times 0.10 and take the square root of all that. If we did the ice chart, made our assumptions, that's what it would come down to. 2.9 EXP 8 negative times 0.1, take the square root, and I get the hydronium ion concentration to be 5.39 times 10 to the minus 5. So the pH here is the negative log of 5.39 times 10 to the minus 5, which is 4.27. Okay, so that's our initial point. So initial point. All right, now let's add in milliliters of the base. So our millimoles of acid initially, that's going to be 20 milliliters times 0.10 molar, so that's 2 millimoles. Now millimoles of strong base added would be 8 milliliters times 0.10 molar, so it's 0.80 millimoles. Okay? Now, millimoles of acid is greater than millimoles of base, so we're pre-equivalency point. So our excess acid is just going to be 2.0 minus 0.80, 1.20. Our millimoles of weak base is just going to be the 0.80. And I need pKa. pKa here is the negative log of Ka. So it's a negative log of 2.9 times 10 to the minus 8. So that's 7.54. So the pH here using Henderson-Hasselbalch is 7.54 plus the log of base concentration 0.80 over acid concentration 1.20. So 0.8 divided by 1.2, take the log of that and add it to 7.54. I have a pH here of 7.36. Okay, so pre-equivalency point, where we had 8 milliliters of base, we have a pH of 7.36. Okay, so now let's add in 20 milliliters of base. If I add in 20 milliliters of base, I now have 2 millimoles of base. I'm at the equivalency point. And so all of my weak acid has now been converted over to conjugate weak base. So our molarity of weak base is just going to be 2.00 millimoles divided by the new volume, which is 40 milliliters. So 2 divided by 40 is 0.050 molar. Okay? And I'm dealing with Kb now instead of Ka. So Kb is going to equal 1.00 times 10 to the minus 14 divided by Ka. So I get a Kb of 3.45 times 10 to the minus 7. Actually, it should be just 3.4. Okay, and our hydroxide ion concentration is just going to be the square root of Kb, 3.4 times 10 to the minus 7, times the molarity, 0.050. So I get the hydroxide ion concentration to be 1.3 times 10 to the minus 4. So our POH is going to be the negative log 1.3 times 10 to the minus 4, which is 3.88. So our pH, 14 minus 3.88, is 10.12. So equivalency point, 20 milliliters of base, we have a pH of 10.12. So all we have to do now is look at a post-equivalency point. We add in, let's go, 30 milliliters. Okay? Now our millimoles of strong base added is going to be 3 millimoles. So we are post-equivalency point. Okay? And post-equivalency point, then I'm looking at excess strong base. So 3 minus 2, 3.00 minus 2.00 gives me 1.00 millimoles of excess base. So my concentration of strong base in excess is just going to be 1.00 divided by the new volume, 50 milliliters, so So 1 divided by 50 gives me 0.020 molar concentration. So POH is just going to be the negative log of hydroxide ion concentration, which is the negative log of the strong base concentration, 0.020 molar. So that's 1.70, and 14 minus 1.70 says that our pH is 12.30. Now guys, the titration problem is tedious, but it's not hard. And you can always back up and do ice charts when you're doing a weak acid, strong base titration curve. Fill out your ice chart and do it that way, or you can take the shortcuts that I've given you here in the notes. And this, guys, ends the section of chapter 17 that has to do with acids. The next section we take on is slightly soluble salts.